Good morning, everyone. We are glad to see you, or whatever feel you, read your names. Before we start, let me address a couple of organizational matters. Oh, it's noisy, but well, I wouldn't talk to them. First of all, it's about the groups. Now, current situation is about 90 students have been formed the groups. That's good. It's about 40 students which are left. So please be aware that it's good to form groups. We still welcome your suggestions. All right, if it doesn't work, we'll try to force you into the groups. All right, that will be good. Also, for those who are already in the groups, I'm trying to arrange first round of presentations. All right, the presentations are supposed to be on Monday afternoons. But well, if it appears that many people have schedule problems for Monday afternoon, we could shift it. All right, anyway, when I write you, it's just proposal for the schedule. We can kind of, you can trade off. Right, also for those who have formed groups and have not contacted the instructor yet, please do so. Even if you are not scheduled, it's good to know, it's good to understand what you have to do for the presentation, and that can only be learned in course of conversation with your instructor. Fine, something else, whatever. Any questions concerning organization? Please put questions to the chat or speak up. Not at the moment. Good, so I will give floor to Miriam. Thank you.
Thank you, Yuli. Good morning, everyone. Welcome to our second problem-solving session. Today, I will discuss with you two problems. They're exercises from the book. There are also exercises on the list of presentations that you could choose. You find them there. I'll refer to them as problem 1 and 3 in chapter 2. What I'll do is I'll discuss these problems step by step. And my hope is to do this in such a way that you also get an idea for how to write down the solutions to the homework that you will get later. So the level, the kind of steps that I will show you in my solution is more or less what we expect from you when you solve the homework problems. It's about the topics from chapter 2 that you heard about in Yuli's lecture last Thursday, the bosons and the fermions. And what we're actually going to do is we're going to solve the same problem twice. First for bosons and then for fermions. So let me see if I can share my screen with you. I made some notes and we'll just go slowly over these notes. If you have questions at any point, please write something in the chat. If I don't reply within reasonable time, please speak up, and then so that you get your question gets attention. So the problems are here. They are about pairwise interaction for bosons, and then in the second half also for fermions. These are exercises that you find in chapter 2, number 1 and number 3, at the end of chapter 2 in the book. And they are essentially a good exercise about how to learn to work with bosons when you are given an interaction Hamiltonian. So we'll start with the bosons, pairwise interaction for bosons. What does the system look like? Imagine, sorry, that was a bit too fast. Imagine particles, bosons in this case, in a system of levels. and let these levels be labeled by an index called n. So let's see if we can draw some levels. If you like, you can also do this for yourself, make your own notes. I'll draw some levels here. So we're considering a system of levels, many of them, n of them, and we'll label them with an index n. So the lowest one here, the ground state, should be level 1, and then there is level 2 here, and we go up all this way until the one but last, which is n minus, doesn't want to do the minus, this is supposed to be a minus, n minus 1, and the last level, the upper one, is n. So there are these levels, and we'll label the wave functions when a boson occupies one of these levels, and the corresponding wave function is given by this psi with subindex n, of course for the respective level, and then r for the position the particle is at. If you like, you can also label it in Dirac notation. Then a particle occupying level n would be given like this. And the associated energy, the eigenvalue, will label as E with subindex n. So this defines our system. And now assume that there is an interaction between the bosons. It's weak and it's pairwise. What does that mean? Well, you'll see the Hamiltonian here, H interaction. It's U, a certain constant, and this U is dependent on R1. Sorry, it's not a constant, it's a function here, sorry. It's U depending on the distance between R1 and R2 for the two particles, the two bosons we're looking at. And we're assuming here that it has a very specific form. It's a constant, U now is just a number, a constant number, times a delta function R1 minus R2. So what does this tell us? What does this interaction do? Well, it's zero almost everywhere. It only acts if two bosons are sitting at the same position. Only then this delta function will be non-zero if they are occupying the same position in space. Then they have to pay a certain energy, U, that costs them a certain interaction energy. So it's a very local pairwise interaction that these bosons are experiencing. Let's see what we can learn about this system. Now, first of all, simple start, we're going to start with only two bosons. Assume there are two bosons in this system. Question asked is, write down all the possible stationary states that these bosons can occupy. And let's do that in terms of the so-called two-particle basis states, Nm, which is nothing but the product of psi n, the boson sitting at R1, times psi m boson sitting at R2. Now, how do you approach a problem like this? There will be many exercises in the course of this semester, in this course, and also often in the exam, where the first question is to you, write down all the possible states. Often, very often in calculations, a useful starting point is to distinguish two cases. Distinguish the case where the levels are actually the same, the bosons are sitting in the same level in this case, and the case where they are not. And then you first solve for this case, and then you think about the case where they occupy different levels. So that's often a useful starting point to distinguish these two cases. So we'll start with the case when n is m, the bosons are sitting in the same level. And then the wave function for the two of them is actually very simple. It's simply the product of the two single particle wave functions. And since they're sitting in the same level, they have the same index n. Psi n, boson at position R1 times psi n, the boson sitting at R2. And shorthand notation can also be this. They're both sitting in the same level n. So that's fairly straightforward. Second case, where the levels are different, n is not equal to m, then the claim is that the wave function should be this. It's a sum of psi n, psi m, plus the other way around, first boson sitting in M and second boson sitting in level N. And again, I can write this in shorthand Dirac notation as Nm plus Mn, and both of them cats. Why is this a correct wave function or the correct wave function? What do you think? Why does it have this form? Why, for example, is not just the first term sufficient? Write something in the chat. Why do we need to do this? Sarah is writing it's symmetric under permutation. It needs to be symmetric, Andrew also. Yes, yes, you are correct. It's a bosonic wave function, so it must be symmetric under exchange of the indices. So therefore, I must symmetrize it. And the only way to symmetrize this wave function is to add the second term where you have switched the positions. Very good. Now, one thing is missing because this wave function is not properly normalized yet. So let's normalize it. We have to put a 1 over square root of 2. Sorry, my program is a little bit complicated. This should be a square root of 2. In front of this wave function, and the same here on the other side. I'll put it behind. 1 square root of 2. Okay, now it's properly normalized. So far so good. We have found the product wave function for this system of two bosons for any combination of levels n and m. So the wave function must be symmetric. And now we have all the ingredients to start calculating matrix elements and corrections to energy levels. So part B is asking us to calculate this matrix element here. There's the Hamiltonian sandwiched between the two particle wave function KL, the bosons in level K and level L, and the two particle wave function MN. And then they're asking us to write this matrix elements in terms of this integral here. And the integral just serves as shorthand notation. We'll find, when we evaluate this matrix element, something of this form, and to write it in a more compact way, there is this parameter being defined so that we can be more practical about the notation. Now, how do you do this? Well, straightforward substitution. You know the Hamiltonian, it's given. And now, since the previous exercise, we also know the two particle wave functions. So we just substitute. Straightforward substitution. Here's the matrix element. And then what KL is just the product of psi K R1, psi L R2, the two particle wave function. The same for Mn on the other end. It's here, psi M times psi N. In between is the Hamiltonian. I've written it straight away in terms of the explicit form it has, U times the delta function. And since it's a matrix element, we must integrate over all space, both for R1 and for R2. So this is our, just by nothing mysterious, just substituting the ingredients we already have and integrating over all space gives us this double integral. Now the delta function reduces the double integral to a single integral. We'll evaluate it, and then we're left with just the integral over R1, say, and there's a product of these four wave functions, and all of them now contain R1, because this interaction only acts if every particle is sitting at the same position. And then we have left, the U was in front, U times, and here you recognize this integral that we were given, here it is. So we can also write this as U, as A, K, L, M, N. Now there is a question in the chat. I'll just look. Will this example exercise sheet be put on Brightspace? Elvis, no, I don't think we'll put the notes on Brightspace, but Yuli for sure will post the video. We're recording this session, so you can always watch the video again. The exercises are in the book, and actually the solution of the first exercise that we're doing right now is also given in the book, so that you can all read about in there. So good, we have the matrix element. Now, having a matrix element, we can go one step further and start corrections to the energy levels. So that's part C, compute the first order correction to the energy levels. And again, we're going to approach it distinguishing the two cases like we did in part A, n is equal to m and n not equal to m. First case, n and m are equal. Then the correction to the energy levels is precisely the matrix element that we calculated in B. And since n is m, it becomes very simple. There's nn sitting on the left, and there's also nn sitting in the ket on the right. There's the interaction Hamiltonian. And if you evaluate this, well, we don't have to do anything because we already did this in B. This matrix element is U times A, and then there's all these indices here. And being a little bit careful about the indices because they're now all the same, we end up with U times A, N, 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 N. And if N is not equal to M, it's a little bit more complicated because you get more terms. The correction to the energy level for N not being the same as M is given by U in front, and this 1/2 comes from the normalization. We normalize the wave function. Let me just go back. Here it is. We're substituting now this normalized wave function in our matrix element. So that gives us a factor 1/2. And then there is a sum of 4 terms, and you have to multiply out all the different combinations that are possible, NM, NM, and then there's NM with MN, and so forth. Each of these matrix elements we have calculated in the previous part in B. So we substitute the solution for them, use the result from B, and you end up with now 2 times U, and then there is again this integral shorthand A, MN, MN. And you can also switch the indices. That doesn't make a difference. It's the same as NM, NN. Yes, okay, Thomas, I see your question in the chat and Elvis has already answered it. That's correct. I should have said the wave functions are real. The wave functions are completely real, so the complex conjugate is the same as the wave function itself. And last part for the bosons, part D, is we're going to extend the number of bosons now. Up to now, we had 2. We were looking at 2 bosons. Now we're going to assume that there are n bosons, and they're all in the same level. Let's say level 1 for simplicity. Again, the question is to compute the correction to the energy levels for this more complicated system. How to approach this? Well, you now need to think about 2 things. First of all, we need a new wave function. We need the wave function for n bosons in one level. And we also need to look at the Hamiltonian, because the Hamiltonian is still pairwise, but now there are many more pairs that have to be considered, since there are many more bosons. So let's look at those 2 ingredients which we're going to need for the matrix element in order to calculate the energy correction. So what is the new wave function? First, write down the wave function for now n bosonic particles. That's actually straightforward because you're still looking at n1 particle wave functions. So now instead of just having 2 indices here for 2 bosons, we need n. These are supposed to be n, capital N indices, and they're all sitting in level 1. So let's label them as 1, 1, and so forth, 1, 4, n times. So it's a product wave function of n single particle wave function, psi1, psi1, R1 up to Rn. So that's still hopefully straightforward. And the interaction, well, it's still pairwise, but now there are more terms. So instead of just having a single term, delta function term in this interaction Hamiltonian, we now have a sum because we must consider all possible pairs among these n bosons. So H interaction n, if you like, is given by U, that doesn't change, but now there is the sum over all possible pairs, I and j, of the delta function, Ri minus Rj. And then what are the small letters here? Well, I and j both go from 1 up to n, so they must be smaller or equal than n, so that's the number of particles. And I must also be smaller than j, because we want to avoid double counting. The interaction between particle 1 and particle 2 is the same as the interaction between particle 2 and particle 1, and you only want to count it once. Now there is a nice mathematical question. How many terms are there in this sum? Think about it for a while and then write something in the chat. How many terms are there in a sum like this? N minus 1 faculty. Some answers are coming up. Let me just look in the chat. I see different answers. N minus 1, 1/2, n times n minus 2 over 2. Ah, it's so many of you are typing. I'm trying to follow. N squared over 2. There are lots of different, lots of different possibilities are being suggested here. N squared over 2. Some of them are correct and some of them are not. There's only one correct answer, so it must be like that. Let me see if I left some space to write. Yes, okay. So the correct answer is 1/2 times n minus 1. So it's actually the number of ways that you can choose pairs out of a population of capital N. So that's n over 2. This is the number of ways I can form pairs when I have n in total n particles. And if you write this out, then it is indeed, and some of you have answered that, 1 over 2 times n times n minus 1. No, this is not a nice bracket. Voila. Yeah, something thinking back to mathematics, and this is what it should be. And once we have this, the wave function for n particles, and the pairwise interaction also for n particles, all we have to do is substitute them into the matrix element, and that gives us the correction to the energy. So this correction, let's call it delta E, the correction to this wave function, the energy of this wave function here, is given by the following matrix element. There's the wave function on the left, there's the wave function on the right, both of them for n bosons. The Hamiltonian goes in between. And if you work that out, it ends up with U times, again, A. All indices are 1 because all the particles are sitting in level 1. And then because of this number of possibilities, there is the 1/2 n times n minus 1. Yeah, so I hope it's reasonably clear. If there are questions, please ask. But this was the last exercise for the bosons. Now let's move to fermions. Yeah, I think there's still a little time left before we take a break. So now I already said we're essentially going to do the same thing, but now for fermions. So we're looking at the same interaction, pairwise interactions, just the type of particle has changed. Assume that there are fermions. Now, one immediate change is that now you need to label the levels with 2 indices, because for fermions, you also need a spin index. So you need one index for orbital as before, let's call it n again, and you need a second index for each wave function for spin. Let's assume that spin is given by sigma plus or minus 1/2. So this now labels our states, n and sigma. And again, we're going to start simple with just 2 fermions. Let's assume that they're sitting in the same level n. Just as for the bosons, the first question is, what are the possible wave functions? What are the corresponding wave functions for 2 fermions sitting in the same level? And then once we have them, also compute the correction to the energy due to the contact interaction. How do you do this? Well, there's now orbital and there's also spin. So it's often convenient to think about the orbital part of the wave function and the spin part of the wave function separately. And the first claim here that I make is that the spin part for this system here, here, 2 fermions in the same level, spin part must be 1/√2, that's the normalization, up, down, first particle has spin up, second particle has spin down, minus the reverse, first particle spin down and second particle spin up. Can you think why that is? Why does the spin part have to be in this form? Yes, Michiel, I think you are, and Douwe also, sorry. Yes, you're both correct. It must be antisymmetric under permutation of the spin indices. And the only way to achieve that is with a minus sign here for two fermions. So has to be oh, sorry. Let me just move this here. With respect to spin indices. Now that's the spin part. The orbital part, that is simply still the product of the 2 wave functions, both of them in level n, psi n r1 for the first fermion and psi n r2 for the second fermion. So if we combine all of this together, you have the total wave function consisting of orbital part times spin part and given by this. So far, so good, 2 fermions. Now the correction to the energy of this state, due to the same interaction that we had before in the previous exercise, contact interaction, that is given by, here it is, delta E, both fermions in the same level, and N is U times, again, this integral, shorthand notation for the integral, A times NN, NN. And the reason that I can write this down straight away is that the spin part that we now have of the wave function does not contribute to the matrix element. And so in principle, I have to compute this matrix element again, and there's the total wave function on the left, and there's also the total wave function on the right. Total means there's also spin part of the wave function now, but my claim is that this spin part you can disregard. You have nothing to do with it, and therefore you can write it down, this energy correction, straight away. It's the same as for the bosons. Now, why is that? Why does the spin part not contribute? Do you have any idea about this? Why does the spin part? I see some other questions. I'll come back to them, but let's first discuss why this spin part does not contribute. Why do I know that straight away? Yes, Michiel, that's very good. The potential, the interaction Hamiltonian, the pairwise local interaction, does not contain any spin. It does not interact with the spin degree of freedom of our fermions. So I can disregard it. It's that part of the wave function just gives me 1 if I multiply it out in the matrix element. So I only have to deal with the orbital part, and that's an exercise we did before. Let me see what I missed. What is the circle with the X in it? Cross product, tensor product. Yes, that's correct. I think it has already been answered. That's a tensor product because these are two different Hilbert spaces, the orbital Hilbert space and the spin Hilbert space. And to combine those two in a wave function, you use the tensor product. Thank you. Very good question. I should have explained. Next part. Now, this is just a spin part that doesn't contribute. Next question, how does this wave function that we now have for the two fermions change if we permute the coordinates of the electrons? Well, that's something we can just look at because we wrote it down. Here it is. If we permute the coordinates for the electrons, R1 and R2, I don't think anything changes at all. So this wave function is symmetric under permutation of coordinates. Let's write something here for completeness. It does not change. So far, they were in the same level, these fermions. Now let's put two fermions, let's consider electrons, into different orbitals, n and m, and they're explicitly not equal. N is not equal to m. Again, the same question as before when the orbitals were still the same. How many states are now possible if we put these two electrons into different orbitals? Does anyone have an idea about that? How many possible states can you write down for this situation? I think in different language, perhaps you know this problem very well. Yeah, I see 4 and 3. The wave function to be antisymmetric. I'll come back to that. 1, no, 1 is not good. No, there are now more possibilities. The orbital levels are not the same. N and M are different. 3 seems to be coming back also. 4, well, let's see. Once I show you the next slide, you will all say, ah, yes, of course. I am actually quite sure that you have seen it before. The correct answer is 4. Someone answered that also. And the 4 are standing for the singlet and the triplet states. Together, they are 4 possible states. And or what do they look like? Well, if you reason, then the reasoning could be as follows. We now have 2 orbitals, n and m. And so all the possibilities that I have for the quantum numbers, combining them with spin, is that total spin could be 0 or total spin could be 1. And if s is 0, then ms, the spin z momentum, is also equal to 0. But if s is 1, then ms can go from -1, 0, up to 1. Together, these are 4 possibilities. And if we write them down more explicitly, then this first spin possibility, s is 0, ms is 0, that is linked to the wave function where the spin part is a singlet part. It's first particle in spin up, second particle in spin down, antisymmetric minus with the opposite, first particle spin down, second particle spin up. And that is combined with the following orbital part because the entire wave function must be antisymmetric. And I think someone asked about that in the chat. So for fermions, the total wave function always needs to be antisymmetric. Parts of the wave function can be symmetric. I think someone asked also about that. This previous question here was just a question about the orbital part of the wave function. How does the wave function change if I permute the electrons' coordinates, the R1 and the R2. So if you only look at the orbital part of the wave function, it can be symmetric. But the total wave function, including spin and orbital for fermions, must be antisymmetric. So that's what you also see here. For S is 0, total spin 0, you have an antisymmetric spin part combined necessarily with a symmetric orbital part. This is the only possibility, if the spin part is antisymmetric, to find an overall wave function that is also antisymmetric. Now for S is 1, there are 3 possibilities. The total ms could be -1, that gives you this spin part. The total s could be 0, that gives you this spin part. And then there is also ms is 1, and that corresponds to both spins being up. And since now each of these spin parts of the wave function is symmetric, you must combine it with an antisymmetric orbital part. And the only possibility here for 2 electrons is nm minus mn. So all of these wave functions, all 4 of them are good fermionic wave functions because they're antisymmetric under permutation of indices. So this gives us the wave functions for 2 electrons sitting in 2 different levels. More possibilities than if they both occupy the same level. And now having the wave functions, we can again compute the energies of the states that we found here, up here, these 4, due to the contact interaction being there. And again, our life is made quite easy because this Hamiltonian does not interact with spin. So actually all you have to look at is again the orbital parts here, this part and this part, and you can forget or you can neglect the spin part in this exercise because it does not contribute to the matrix element. Singlet state, again, the spin part does not contribute. You find, same as we had before for the bosons, 2 times U times AMNMN, 2 different indices here because they're sitting in 2 different levels. Same calculation as before for the bosons. And for the triplet state, the correction to the energy levels is 0. Why? Well, the triplet state is here. The reason is that it's antisymmetric in orbital. So any contribution I get from this ket, NM, I also get from this ket, MN, but then with a minus sign. So in the end, everything cancels and the correction to the energy levels is 0. Now, I think I'm almost at the end here. I have answered my own question. So let me just see if I can write it here. Okay, it does not seem to do anything. Well, okay, maybe we'll leave it open for now. So the correction is 0 because the orbital part is antisymmetric. That already concludes the second exercise. Let me just see if I missed some questions in the chat. Why should the wave function be antisymmetric? I hope that is clear now. For the fermions, Sasha, so the total wave function still switches sign under permutation. Yes, it does. Yeah, yes, it does. You can see that here, for example, if I permute the indices here, then I get a minus sign in front. That's correct. And I think that was the last question. Any more questions? Please type if I've also missed something. I hope I haven't, but I'm not completely sure. No? Okay. Okay. So I'll hand back to Julie. Thank you very much.
Thank you, Miriam. Good. Let us see. I wonder what we can do. We still have quite some time. So last time we didn't have time to talk about density metrics. Okay, there's a question about presentations. I will answer it. Why don't we talk about density metrics now? Sir, I would think that you need a break, like 10 minutes perhaps, and we can talk about density metrics if you wish. And let us see, there's a question, right? It's a no. Miriam, I guess there's one question to you and another question to me.
Okay, okay. Let me just have a look.
If I understood correctly, or yeah, the last question is to you.
Is this the format?
Or is it an answer?
Is it an answer? Let me see. I have to read it. Same as the anti-symmetric. This is symmetric. Yes, yes. I think it's an answer. Douwe, that's correct. I think it's an answer to a previous question. Okay. Yes. Okay. Very well. I think it's been solved.
Good. So let me answer the question of Francesca. Is this the format of the presentations we are supposed to give? No, not really. First of all, your presentation is supposed to be already from this detail. I could figure out that your group hasn't talked to instructor yet. Okay, good. It's good to talk to instructor. As to your question, no, of course not. First of all, your presentation is about 15, maximum 20 minutes. Second, it's a more standard presentation, like with PowerPoint slides. And yeah, it has to be kind of, it shouldn't go much over technical details, although technical details which are needed have to be present, but it has to be shorter and more kind of presentational presentation. I don't know about you, Francesca, kind of Dutch students are well trained in doing presentations and doing together in the group. So kind of they usually know what to do. It's to some extent it looks like a traditional school presentation, but well, about advanced quantum mechanics. Right, so let's have a break for 7 minutes left. 9:35. I will talk about density metrics. Thank you. Good. Let us go on. Let me talk about density metrics. And what I do, I just don't go through slides, but we'll try write everything down rather slowly. And I want to say that upon my observation, the problem with density metrics is somehow the problem of notations, which have little to do with density metrics, but rather with the fact that quantum notations have been introduced quite some time ago. They are kind of half forgotten. And despite the fact that we have refreshed it a bit, let me just do it again. So let us see. I hope that this works and you see everything. So let me just start with a wave function. How we can write it down? We can just write a cat. An abstract vector in the Hilbert space. We can also write it in terms of components as a function of x. In this case, we are talking about continuous Hilbert space, a basis which is labeled by continuous numbers x. And you know what it is formally? There is a basis for each x, and we do in a product. Good. So very theoretically, these and these are different objects. For mathematicians, perhaps, yeah, but not for physicists, right? Because what we can always make use of, we can go from one basis to another basis. So if we know wave function in a x basis, x presentation, we can go to any presentation we use. So how to do it, for instance, to go to another presentation for wave function. First, we need to choose basis. Since we are in X representation at the moment, let me choose basis functions. I will call them chi and of x. By the way, I have forgotten to mention that x can be one-dimensional number, can be multi-dimensional, can be a vector, 3, 4, 5, 6 dimensions, whatever you say. Right, so those are basis functions of some basis, and it's labeled by n. for a change, it's a discrete number, could be continuous number as well, but that's the association we found. Right. If there anything, so don't hesitate to ask any questions, even if it is about a material which you have learned many years ago. Then it's really time to ask a question. Okay, so put questions to the chat, or you could speak up if you wish. Right, so there are wave functions labeled by n new basis, well, with the same kind of accuracy of notation. I could just write it as n, skipping letter k. And I can write now the same wave function in new basis. I can use this rule. So let us see how would it go. I will have components which depend on n. And I will make them as usual. Oh, that's abstract. Now let us figure out how to write it in X representation to enable kind of practical calculation. Right, maybe a very basic question, but what is the main idea here? Why we are projecting psi in X? The idea is to illustrate that wave function, again, it goes something about representations of wave functions. It is, the idea is to show that wave function, which is a vector in Hilbert space, can be presented in different bases, right? So X is an example of a basis. One could think of coordinate space. One could think of, actually, one could go crazy and call it momentum space, right? It's just only notation. What's important that there is a basis of wave functions, basis, which is labeled with X. Right. What is chi here? Chi is another basis. For a change, it is labeled by discrete index n. So I'm going to show how to express components of this wave function in chi basis. Because I'm sure you have seen these formulas, but sometimes there's some mixture, a quantum superposition of different formulas in students' mind. All right, good. So I am trying to express psi in new basis of chi. That's what I'm always going to use. This is formula of projection. It works for two-dimensional vector in space, just for geometry. It also works for vectors in Hilbert space. Good, but that's abstract. So how can I utilize it and write a concrete formula, what I have to utilize, let me know to this. So, the expressions for basis vectors and for wave function in a certain representation. Okay. So I guess you can guess what I'm going to write, but let me do this. It is a summation over all basis vectors of X. Since it's continuous, I replace summation by integration. Then it goes with conjugation. Nice to remember. Yeah. And here we are. So this is a formula for this abstract in a product, in concrete terms, in terms of integration. If X were discrete, not much change would happen. One could always kind of discretize continuous basis. In that case, it would be sum over X. Well, as you see, it's almost the same. Good. So that was about wave function, about different representations. We are not yet at density metrics, but from my experience, one has to say it, one has to refresh it before going further. All right. I sincerely hope that we kind of make it clear. Please, any questions at this point? Okay, then I will try to go a little bit further. How does chi n relate to n in the last line? That depends on the concrete structure of the basis. Let me take, for instance, the basis of particle in potential with infinite walls. There are nice functions and solutions of the equation. I hope you remember, we have repeated it. And they form orthogonal basis. So let me take this as K basis. It will work for all functions which are somehow squeezed into this interval. All right, why do I choose it? Because I remember by heart how these functions look like. And in this case, I hope I won't make an error in normalization factor. Chi of n of x is, there are different sinuses and x divided by L pi. Now I need to recall normalization factor. So it is average modulus is 1/2 integrated over L. Yeah, L is here. So it's 2 divided by L. So this is normalization factor. It is the same for all bases, all the basis functions. All right, so this is an example again. One can take wave functions of a particle in the box. One can take wave functions of harmonic oscillator. One can take any orthogonal wave functions which you can imagine. All right. So in any choice of basis, you will be able to express the answer in terms of the components in this basis. Fine. Let me go on and let me talk about operators. And now I guess it might be a bit shocking, so prepare for this. Operator. So let me take an arbitrary operator. A stands for arbitrary. So what operator does is some, if you wish, procedure, linear procedure. So operator acts on a wave function and it returns, let us consider it as a computer subroutine. It takes wave function as input, it gives output, which is another wave function, similar vector in Hilbert space. So one can talk about matrices because matrix the object which takes vector and returns vector is a matrix. That's what we recall when we talk about matrix formulation of quantum mechanics. Let us see. Let us make this matrix explicit. First, in discrete basis, let us talk about matrix elements of this operator in a certain basis. What are they? I guess you know these. It's the same operator, which is kind of bounded, bracketed by corresponding wave functions of the corresponding basis. So n comes here, a here, m here. All right. Good. So we get matrix elements. Let me try to get back to X representation. That's perhaps the shocking experience. Let me choose X instead of basis. Right. Then let me rewrite it. So I put one of X's here. And other X here. Could put X1, X2, doesn't matter, just notations to certain values from X manifold. Right. But what I have here, it's a function of two variables. I saw many students who kind of didn't get enough experience with this point. Thereby, I can show you this experience. Let us understand that each operator in coding representation is in principle a function of two variables. Because operator has two ends, bracket. Fine, let me try to write something. Okay. How can I, for instance, now write this in X representation? I could do formally, I could project it to operator X, but I guess with our experience, we can write it right away. So in the, yeah, I'm talking about this equation. I would like to rewrite it here. How shall I start? It is chi. And since we are working on in X representation, it should depend on X. It does. Fine. Then I need to write this. Let us see. What do I write? Let us see. Let us follow that everybody understands this. What argument shall I give to function psi? Who can answer? Yes, very good. Very good, Sarah. X prime. That doesn't look close to linear algebra. To rewrite this as a linear algebra, I shall replace integration by summation. Then it looks more kind of familiar. More familiar. Oh. Did something wrong? It looks like I just discard. Oh, no. I guess I have it here. Right, just a second. I will share it. Just a sec. Very small window. Here we are. So now it's a matrix which depends on two indices, the same as function, just without this curly bracket. So now it's in traditional notations of linear algebra. Good. Let us multiply operators. So how we do this in different bases. Say if it is a discrete basis, right, we would multiply matrices, and I hope you remember this: index n, index m, and the b comes, yeah, here it must be the same index, and here, let me put it, summation over m. Sometimes people, to speed up, do not write summation if indices are repeated. They assume that in any case there's a summation over these indices. Fine. Look, if I do the same in coordinate representation, sorry, in X, no, well, okay, the same coordinate representation, but in any continuous representation, I would have to replace summation by integration. So what I would have, let's see. So that is instead of index m. X will be instead of index n. And b is instead of index x prime goes instead of index. Okay, all right, that's how we multiply the operators. So we can do it at subject level. We also can do it in any basis, either discrete or continuous. In continuous basis, we employ integration, and each operator is a function of two variables. Fine. Good. Any questions? If not, I can switch to density matrix, it seems. Right. It's kind of funny notion. In fact, if you look at applications, if you try to understand quantum mechanics of real systems, quantum mechanics which is readily measured, most likely you would have to deal with density metrics rather than with wave function. Because the notion of density metrics is more general and more flexible to describe real experimental situations. So as we discussed, there are two main definitions of applications of the same concept of density metrics. It might be surprising, but quantum mechanics is full of complementary stuff, right? It has many pictures. The same quantum mechanics can be understood in many pictures, so there should be no wonder So the same concept, density matrix, can come from two facets, right? These two facets eventually describe different experimental situations. Let's see how different. First of all, statistical ensemble. And what is this? It's a bit like a fish in a pond. Right, let me draw a pond. Oh, something has happened with my, oh yeah. And there are quantum systems in the pond. So how the experiment goes? We're trying to measure quantum state of these fishes in the pond. So what we do, we catch one and measure it. We know that in quantum mechanics, measurement is obtrusive, right? So after we measure it, the fish is dead. We could not measure it again. We would not produce any more information. So let us see. For instance, we can measure. Let me talk about qubits. Let me talk about simplest example. Let me talk about two-level systems with fish. Yeah. In this case, measurement outcome can only have two values, 0 and 1. Fine. So I feed these qubits, and after long run, after measurement, I would come up with distribution. That would be probability to catch 0. And that would be probability. Okay, let's make it simple first. I measure 0 and 1 with equal probability. So what does it mean? It depends. It depends whether I know that all fishes in the pond have the same wave function. In this case, we are talking about pure statistical ensemble. Right, and if I measure this and I know that ensemble is pure, what can I conclude? I would say that there is some wave function which has equal weights for 0 and 1. Can write it as a vector. That could be this vector. Or perhaps this vector. There are many possibilities which differ by the phase, relative phase of two elements of the wave function. Okay, this wave function is in x direction, this is in y direction. In this experiment, we cannot distinguish between these two. One could make other experiments, for instance, measure in x direction to distinguish. Yeah, it is under assumption, under using extra knowledge, that all the functions are the same, that ensemble is pure. But what can be a very practical and different situation? It can be, let me draw the plot again. That some qubits, each qubit has a wave function, and some qubits have wave function with spin up, and half of them have wave function with spin down. Right? With measuring, basically, I don't want to redraw this plot. That's what we get. That's what we get. Equal probabilities to have 0 or 1 projections on the z-axis. Right? One could make another measurement, the measurement along other axis of the qubit. One could distinguish between the cases, but I'm not about this. I'm about characterizing all possible states of the ensemble. So we just figure out that ensembles can be non-pure. Right, and kind of the quick idea, which appears to be useful in larger context, is to make a kind of is to take wave functions with different with weighted by probabilities to have it in this ensemble. Right, so I will write it in general, density matrix, and we'll make it from probabilities and wave functions of some basis. To describe, for instance, this situation, I have to take equal probabilities with 1/2, and wave functions either 0, 1 or 1, 0. Let me write it now in as a matrix. As we have seen, it looks almost like an operator density matrix. Mathematically, one can multiply it as an operator. It could even work in wave functions as an operator, but it's a density matrix. Operator presents in quantum mechanics a quantity, but density matrix, like wave function, it presents the state of the system. All right. So how would I write it? It as a matrix? Well, it is like the following. It is diagonal matrix because qubits can be in only one in basis states, right? That's an example. Let me get to, okay, let me call it impure. Let me get back to this example. Let me provide density metrics for pure ensemble, and that would be each. Let us see, now I have to normalize it, so I divide by 2. Good, so there is a difference. These two different situations are described by 2 different density matrices. So this is yeah, simple example how to define a density matrix as an element of statistical ensemble. It is related to a concrete experimental situation. Although very general one. It means that we have a pond, a reservoir, whatever, of different quantum systems, and measure it one by one. If you're working with big ensembles of particles, which are supposed to be in the same or similar or different quantum states, that works perfectly. Any questions about this? I couldn't say everything about this, but perhaps you have a question which I will be happy to answer. When I do it offline, usually have a rule. If nobody asks questions, I ask questions. But well, it would be stupid to do something like this in Zoom. Let me then play yet another game. Let me ask questions and answer it by myself. Let me ask a question. Well, it is a discrete spectrum. I understand it's finite size matrix. What would be if the spectrum is continuous? Well, I can use the fact that the matrix is similar to operator. Sure, in continuous representation, I guess I have to start next page. It's always kind of difficult to do this in Zoom. Let us see. All right, that worked. Right, sir, that would be function of two variables. So this is density matrix as contrasted with wave function. Wave function has one variable, density matrix has two. Let us see a question from Sar. Am I to understand that in the second state we have two kinds of particles with either 0 or 1. And in the first case, you have a pure state which is in a superposition. It's really quantum question. One can actually answer it like this, but let me just spell out all possible variants. In the second state, we have, that depends upon what you call kind. We have particles, qubits, in two different wave functions, in two different states. In principle, one can switch it, take a particle and switch it from one state to another state. So it's not a kind. All right? It is rather a state. So we have particles in two sorts of states. That's second case. In the first case, we have the particles in all the same state. They supposed to have precisely the same wave function. Whether it's superposition or not, it's not important. To describe equal weight experiment, equal weight measurement outcome, I have to assume that this is in x direction, not like this, but perpendicular to those. That's how you count Criterion. It can be, first example was a pure state, although a superposition, and another example, second example was mixed state, but wave functions were not superpositions, they were wave functions of a certain basis. Right. More questions about previous slide? Sure. Density matrix for continuous is just a function. So, for instance, let me get some life to abstract formulas which I wrote. For instance, there's a formula which I like, which many people actually like it, not only me. It is a criterion of pure state, and this is that rho squared equals rho. Very funny. If you think of numbers, you can only have two solutions, 0, 1, right? For density matrices, you can have many continuous number of matrices which satisfy this relation. All these matrices are pure states. One can understand it in terms of this representation. So that's pure state. If we make squared, let me make it explicitly. There's a 1. There is another one coming. But this is 1. So we are back. To original matrix. Good. So how to write it down in coordinate representation? Well, it's a bit lengthy, but again, it is pretty trivial. It's again multiplication of the operators, which I can write as an integration. Okay. So if you know matrix in coordinate optimization, now we can check whether it's pure or not. Yeah, rho squared equals rho holds only for pure state. So the first example of the point where all particles were in the same state. What I also want to mention, that perhaps would be rather short during the time limitations. It is a definition which looks pretty abstract, and this is partial trace. Right. What kind of experimental situation we can imagine? Well, we revert, we observe a qubit. So we are only interested in this qubit. But the qubit is an environment. I don't know. Air molecules, electromagnetic radiation. There are very, very, very many other degrees of freedom which interact with qubit. And we don't know its wave function because it's a wave function in awful many variables. Let me give, since I'm with the qubit, I can write this wave function. So again, I assume that everything is in a good quantum state. So there is entanglement of the qubit with the rest of these things. Okay. The rest, I would denote by a function in many. Okay, I define Hilbert space of all these noticings. And I have wave function in this space. What would be wave function of the whole system? I can have now wave functions in the products in the product of Hilbert space. So there is an example. Qubit is always in a state 0, and there is some very tricky wave function of the environment. Another example. Is here. Good. If by some chance I would have only such functions, well, I could say that I don't care about this environment. I always have a qubit in the state 0. But that frequently doesn't work. Oh, my pen is gone. Anyway, now my handwriting drops a bit. I have to write with a finger. True wave function, let me call it W, is now a superposition of this kind. Right. Let me put coefficients of the superposition. Y is the wave function of the environment different for 0 and 1. If the environment and qubit have been completely isolated, they can be the same. But environment interacts, qubit interacts with the environment, which means that if you change the qubit, the environment will be affected so that it will acquire different wave function. In the first row in black, I give examples of the wave functions. So there is a wave function which consists of qubit and the wave function of environment. It's a product of the two. Those are product wave functions. And if, for instance, there were no interaction, it could be very useful and practical wave functions. With interaction, the actual wave function, for instance, in ground state, is rather this W. Okay, no way to work with this wave function practically, right? And I don't care about all these degrees of freedom. I want to look at my qubit only. To characterize the qubit state is not possible with a single wave function. And what one can do is density matrix, which is defined as partial trace. So in this case, it is a trace of this of the whole wave function over all variables of environment. Right. So after you sum up it, you don't get wave function, you get 2 by 2 matrix with 4 elements. I'm sorry, I'm out of time already. So I hope I can give you, perhaps without much formulas, some feeling of that, of 2 different concepts of density matrix. If there are more concrete questions, please mail to me. And now I will stop the recording.